Welcome folks, a video today on advanced techniques of integration. In this video, we're going to be talking about integration by trigonometric substitution. I'll give you an overview and just do a few examples. So here's the main guts of the overview, starting with, again, what I've been referring to as the mother of all trig identities, cosine squared plus sine squared equals 1. We can use one of three different identities to simplify sums or differences of squares to a single term. Here's the idea. If we see a term of the form a squared minus x squared, thinking of the substitution 1 minus sine squared theta is cosine squared theta, we'll try the substitution x equals a sine theta. If we see a sum of squares, a squared plus x squared, thinking of the substitution 1 plus tangent squared theta is secant squared theta, we'll try the substitution x equals a tangent theta. And finally, if we see a difference of squares of the form x squared minus a squared, thinking of the simplification secant squared theta minus 1 is tangent squared theta, we'll try the substitution x equals a secant theta. These are best illustrated just with a few examples. So here's the first example. Let's go ahead and have a look at the integral of 16 minus x squared square rooted divided by x squared dx. So here we see a difference of squares of the form a squared minus x squared. So we'll try the substitution x equals a sine theta. Okay, so making the substitution x equals 4 sine theta, we see that dx is 4 cosine theta d theta, and we can substitute the entire integrand into theta world here, replacing x squared in the numerator and denominator with 16 sine squared theta, and replacing dx with 4 cosine theta d theta. Now we're just going to make the assumption that our thetas are always in the range where our quantities turn out to be positive, so we'll express the numerator here as the square root of 16 cosine squared, which simplifies nicely, and we'll express the denominator sort of similarly. So again here, just assuming that our cosine term always turns out to be positive, this isn't always true, but for the most part it is, and we'll go ahead and make that assumption. We see that the integral reduces to the integral of cotangent squared of theta d theta. Now we didn't explicitly talk about integrals of cotangent squared, but we did talk about integrals of tangent squared, and you might imagine that a similar strategy applies for the integral of cotangent squared. We're going to replace the cotangent squared with cosecant squared minus 1. So under the substitution x equals 4 sine theta, we see that our new integral can be expressed as the integral of cosecant squared theta minus 1. Okay, so here's that indefinite integral. 16 minus x squared square rooted divided by x squared dx can be rewritten as the integral of cosecant squared theta minus 1, again under the substitution x equals 4 sine of theta. Of course, cosecant squared integrates as minus cotangent theta, and minus 1 just integrates as minus theta. But we're not done yet because we need to go back to x world. And the key to going back to x world is making use of this relationship between x and theta given by our original substitution. As you might imagine, this relationship implies some right triangle out there in right triangle world that allows us to solve for different values of theta given that x is 4 sine theta. So here's that right triangle implied by the relationship sine of theta equals x over 4. Of course, x being the opposite side to the angle theta and 4 being the hypotenuse. We can solve for the adjacent side, which is given, of course, by the square root of 16 minus x squared, and that'll allow us to identify the cotangent of theta. Of course, the cotangent of theta is given by adjacent over opposite. So 16 minus x squared square rooted minus x. And of course, if sine theta is x over 4, Theta is arc sine of x over 4. And here's our general antiderivative written all in terms of x. Okay, super. Let's do another example. Here's another example. Let's go ahead and have a look at the integral of 1 over the quantity 9 plus x squared all cubed, all square rooted, dx. Okay, again, here we see a sum of squares motivated by our substitution before. We'll try x equals a times the tangent of theta. So we can see under the substitution x equals 3 tangent theta that dx is 3 secant squared theta d theta, and our integrand of 1 over the square root of the quantity 9 plus x squared cubed dx becomes the integral of 1 over the square root of the quantity 9 plus 9 tangent squared theta cubed times 3 secant squared theta d theta. Now it looks like life is worse, but again, our strategic substitution here is designed to reduce the sum of squares to a single term, and it exactly does that in this case. In this case, we see that our substitution 9 plus 9 tangent squared is replaced by 9 secant squared. Simplify, simplify, simplify. Of course, the square root of a cube is the same as the 3/2 power. And when we take secant squared to the 3/2 power, we get secant cubed. When we take 9 to the 3/2 power, we get 27. And we're left with 1/9 times the integral of cosine theta d theta. So again, summarizing here under the substitution x equals 3 tangent theta, we can see that we're left with 1/9 cosine theta d theta. This integrates quickly as 1/9 sine theta. Now, similar to before, we need to still go back to x world. However, our relationship between theta and x given by tangent theta equals x over 3 again tells us a triangle out there in right triangle land from which we're able to compute the sine of that angle theta. So again, here's our right triangle implied by our trigonometric relationship with opposite side x, adjacent side 3, hypotenuse 9 plus x squared square rooted, and we can see quickly what the sine of that angle is, the sine of course being opposite over hypotenuse. So here's our general antiderivative in this case, 1/9 times the quantity x divided by the quantity 9 plus x squared square rooted plus an arbitrary constant. Okay, here's another example. Let's go ahead and have a look at the integral, the square root of x squared minus 9 divided by x cubed dx. Again, here we see a difference of squares, x squared minus a squared, motivating the substitution a secant theta. So here's our indefinite integral after the substitution x equals 3 secant theta. Of course, dx is 3 secant theta tangent theta d theta. We can replace x squared minus 9 by 9 secant squared theta minus 9, which eventually ends up as 9 tangent squared. The denominator, of course, is 27 secant cubed theta, and the dx portion becomes 3 secant theta tangent theta d theta. Let's go ahead and simplify this integrand. So at the end of the day, after simplifying our secants and tangents into cosines and sines, we see that we end up with the integral of 1/3 sine squared theta d theta. Let's go ahead and summarize here. Now we know how to deal with all even powers of sine or cosine. We know that we need to use a half angle formula. So here's that half angle formula. Sine squared becomes 1/2 minus 1/2 cosine 2 theta. We can integrate that pretty quickly to obtain a term involving sine of 2 theta and also a term involving theta. So with the additional substitution, sine 2 theta over 2 equals 2 sine theta cosine theta, we can see that we can write our general antiderivative as 1/6 theta minus 1/6 sine theta cosine theta. Now, of course, one more step to get back to x world here, a triangle involving a secant of theta whose value is x over 3. So here's that triangle involving the hypotenuse x, the adjacent side 3. We can compute the opposite side, which is the square root of the quantity x squared minus 9. Of course, theta is just the arcsecant of that angle. And we can also see that replacing sine and cosine by opposite over hypotenuse and adjacent over hypotenuse gives us a quantity 1/2 times the square root of x squared minus 9 over x squared plus an arbitrary constant. Okay, one more quick comment. Here's an example that illustrates a useful technique called completing the square. So here's that technique of completing the square applied to this denominator, which is of the form negative x squared minus 2x plus 3. I'm going to first factor a minus sign out and just deal on the positive coefficient quadratic, which I complete the square to express as the quantity x plus 1 squared minus 4. Reincorporating the minus sign, we can now express our integral as a sum or difference of two squares. So the form of this difference of two squares suggests a substitution to start with, u equals x plus 1. Under that substitution, we can see that we're left with the integral of 1 over the square root of 4 minus u squared du. That now suggests a substitution u equals 2 sine of theta. So under that substitution, u equals 2 sine of theta, which is again motivated by the difference of two squares here, a squared minus u squared. We see that our integrand becomes 1 over the square root of 4 minus 4 sine squared theta times 2 cosine theta d theta, which quickly simplifies as just 1 d theta. So let's go ahead and summarize that. So here is that indefinite integral. Really simple in theta world, we just end up with theta plus c. Now to get back to x world, we're going to use a couple substitutions here, substituting u equals x plus 1, and then of course making use of our trigonometric relationship that u is 2 sine of theta. So again, here's that triangle implied by sine of theta equals x plus 1 over 2. It has an opposite side of x plus 1, a hypotenuse of 2, and we can see that theta has to be the arcsine of x plus 1 over 2. That's the value of the indefinite integral in this case. Okay, folks, hope you've enjoyed this video on trigonometric substitution. Have a great day, and we'll see you next time. Bye-bye.